Okay, this is day 33. We are really starting to come down the home stretch. Today we are talking about one of our last hypothesis tests, and that is the ANOVA hypothesis test. So ANOVA stands for Analysis of Variance. This I like to think of as an extension of our two-sample t-test. Going over a few of the tests that we've done so far, we've worked with both categorical and quantitative variables, and this is an incredibly important distinction to make. The first thing that you should do when working with a question like this is to identify if we're working with categorical or quantitative variables. That's going to dictate everything moving forward. Early on, we started off by looking at a single population, always comparing that to some baseline value. We then expanded this so that we were comparing two populations to each other. On Monday, we started working with chi-squared tests, which are ways of working with counts of numbers of individuals that are in a certain category, where there are several different categories. So here we're working with many populations, or many different categories. Today, we're talking about ANOVA, which fills in this last square. The idea here is if there are several populations and we're measuring quantitative variables, how can we identify that the populations are actually different? So for an ANOVA test, our null hypothesis is typically going to be that the population means for each of our different groups are the same. So what we're testing for is a difference. Our null hypothesis is that there is no difference. Back when we did two-sample t-tests, I used the example of comparing lengths of Twizzlers to lengths of red vines. So length is a quantitative variable. If we have two populations, as in the population of red vines and the population of Twizzlers, our null hypothesis might be that the average lengths of these two populations are the same. And we run a hypothesis test by taking samples and seeing if those samples have substantially different averages. For ANOVA, we're doing something very similar, but we're saying rather than just two populations, what if we have three or more? So let's say we have red vines, Twizzlers, and the store generic. So here our null hypothesis is that the average length of each of these types of candies is the same. And to test this, we're going to take a sample of each of the populations and look at what we see. So let's say that this is what we get. For each population, we take a sample and we plot their length across the x-axis. So this is one way of visualizing the information. We could also use something like a box plot, but I really want to emphasize here where exactly these points are. Just looking at this data set, I'd say that it isn't actually very conclusive. Yes, the average value for the x2 sample is bigger than the average value for the x1 sample, but we can see that this distribution of the sample for x1 has a lot of overlap with that of x2. And this really is true for x3 as well. Let's imagine what would happen if we got different results instead. So instead of this first data set, let's pretend that our results are this second data set. So just by looking at this picture, I get the impression that our null hypothesis is not true. This seems like evidence that at the very least, the average of population 1 is different than the average of population 2. At the very least, it seems like our null hypothesis is not correct. So what's different about this picture? Well, the averages are actually the same distance apart. The positioning for average of x1, average of x2, and average of x3 is the same in the top and the bottom. So what is different? Well, the difference is in the spread of the data. In this first picture, there was a lot of overlap between each of these groups. In this second picture, there's far less overlap. So that's the feature that we're going to key in on when doing this ANOVA. We're going to be comparing where the variance comes from. Okay, so here's the idea behind analysis of variance. If we look at the collection of all of our data points, in other words, if we sort of push them all together, we can look at the spread of our whole data set. In other words, we could find its standard deviation, we could square that and find its variance. So the variance is a measure of how spread out all of these points are. The idea is that there are two sources of this variance. There's the fact that in each of these groups, our collection of data points is spread out. And separately, there's the variation between groups. In this example, the collection of all of the samples is fairly spread out, but I would say that that's largely because in each of the groups, that sample is fairly spread out. So the bulk of the variance that's happening here is due to the variations within a group. So because there is a reasonably large variation relative to the separation between these different means, we can more easily attribute the fact that these means are different to natural variations in the individuals. The main factor in this picture is that individuals have high variance regardless of what group they're in. For this other picture, I'd say that the opposite is true. And we can imagine pushing these data sets together and talking about the variance in this whole picture. So there's a certain amount of variance in our collection of samples. The question is how much of that is attributed to variation within a group versus the variations between the groups. And for this picture, I would say that there is comparatively little variation within the group. That when we look at the total variation in our picture, the fact that we are as spread out as we are is largely due to the fact that each of these groups are fairly far apart. As with all of our hypothesis tests, our null hypothesis is that nothing interesting is going on. Typically, our sample is going to at least somewhat disagree with that. In our sample here, the sample means are certainly not all the same thing. So the question that we ask, the question we always ask, is this difference that we happen to see in our sample sufficient evidence for us to say that the null hypothesis is wrong? Put another way, assuming that the null hypothesis is correct, what is the probability that we get a sample that looks like this? Well, when we say a sample that looks like this, we need to make that more concrete. We need to come up with a measurement for how definitive a sample is. This, I would say, is a fairly definitive sample. We want to put a number on that. The way that we do this is called the F statistic, which, like chi-squared, is just a measurement of how notable a sample is. So to find this F statistic, we compare the variance between the groups to the variance within a group. In the example that we have here, we have a fairly large variance separating the groups compared to a comparatively small variance within the groups. So in this case, I would say that we have a high denominator, but a lower numerator. This results in a large number for our F statistic, our measure of how notable a sample is. In contrast, our first example had a lot of variance within the groups, so a large denominator, and really the same amount of variance separating the groups. So the difference is that the denominator has gotten a lot larger. This is going to result in a smaller F statistic. The question we're always asking with the hypothesis test is, what is the probability that this just happens due to random chance? A large F statistic is saying that this is a very notable result. This is unlikely to happen just due to chance, that there is a very small probability that a situation like this arises just due to random chance. In contrast, if we have a small F statistic, that's saying that, you know what, this thing happens fairly often. We have a large p-value. So in this first case, I would likely fail to reject the null hypothesis, whereas in the second case, I would reject the null hypothesis. Okay, let's look at an example with some actual data and talk about some assumptions that we'll make for these ANOVA tests while working through this question. So what we have here is a data set that came from testing various insect sprays. So we have a total of 6 different sprays, A, B, C, D, E, and F, and they're tested through some experiment. And the thing that we're measuring is how many insects we see, despite there being some sort of insect repellent spray there. So just by looking at this, it seems like A, B, and F do worse, as in there are more insects still around, than C, D, and E. Well, the question we have is, is there some sort of effect going on here? Like, is this a statistically significant difference? To the eye, yeah, it certainly looks like it, but we want to check that. We want to run an ANOVA test to determine significance of this difference. So I want to point out that we know that we want an ANOVA test because we're working with quantitative variables. We're talking about the count of number of insects across many different groups. We have a total of 6 different groups. In theory, we could ask 2 sample t-tests for each of the individual pairs, but A, that gets very cumbersome, and B, that opens us up to a fairly likely type 1 error, as we saw with our jelly beans discussion last time. Okay, let's talk about some assumptions for our ANOVA hypothesis test. Our first assumption is one that really should feel familiar at this point. You might be able to guess it, and that is the independence assumption. We want to make sure that the groups are all independent of each other. And again, there's no way to go back and measure this. This is a question about how our data was collected. So assuming that we had all the right considerations in terms of designing this test, designing this experiment, we can assume the independence assumption. Our second assumption should feel familiar, but we're using this in a slightly new context. This is the equal variance assumption, which on its face is saying that we want the variances for each of the groups to be roughly the same. And when I say roughly, I really do mean, ballpark the same variances. By itself, the difference in variance between F and E maybe is worth noting, but isn't a reason to throw out the test by itself. The piece that we particularly want to pay attention to is, does the variance change systematically with the centers? And what I mean by that is illustrated with this picture. So in this picture, when we have low centers, as in when the middle of these box plots have low values, that also corresponds to lower variances. Higher centers have higher variances. This is a red flag. This is an example of something that does not meet the equal variance condition. The main piece here is less about the fact that we have variances of different sizes, which is somewhat problematic but isn't terrible. The main problem here is the fact that the low variances also correspond to the low centers. So this is an indication that maybe we should be rescaling our data. Maybe it's less about the total count, and maybe we want to be talking about the log of the count or the square root of the count. So let's try one of those. Rather than making the box plots of the count, let's make the box plots of the square root of the count. Mostly I'm using square root rather than log here because one of the counts is 0 and log of 0 does weird things. But the essence is the same, that we are condensing our data set in some way. So notice that now in this picture, yes, maybe F has the largest variance, and E and D have smaller variances, but for the most part, or roughly speaking, I would say that this meets the equal variance condition. Our last condition is the normal population assumption. This is saying that in each of the groups, the population should be normal. Again, this is the nearly normal condition. We just want to check to make sure that it makes sense that the population is normal. If we happen to get a sample that isn't quite normal, it still might be reasonable that the population still is. So again, all we're looking for here is something that is notably skewed or notably bimodal. If instead, like for group C, it's a little bit funky, that's okay. We're really just looking for the big red flags. So one thing we can do is go through each of the different groups and make a histogram of the sample for that group, and just check that each histogram looks nearly normal. This histogram for C, I think, is still good enough. So we're ready to run the test. Like with the LM function to find the linear model, the AOV, the analysis of variance function, is going to return this object, this AOV object, that we can give a name. So we can call this my ANOVA, for example, and then we can run summary on that. We could also just run summary of AOV of this. Okay, so this result that we get is called the F statistic table, and this has all the information that we need, all the information that we theoretically could have calculated by hand, but is certainly not worth doing. Okay, it's really easy to go right for the p-value. We can see a p-value of virtually zero, so something incredibly small, is saying that there almost certainly is something going on, that this is a great reason to reject our null hypothesis, that we don't actually think that all the sprays are the same. We think that there actually is some sort of trend, which certainly agrees with our impression of what this data is telling us. But I also want to talk about how we got this. So this F statistic comes from the ratio of the variance between the groups to the variance within the groups. If we divide 17 by 0.39, we should get about 44. As with our chi-squared tests, we want to be able to convert 44, so 44 is sort of the score, this is how notable our example is. We want to convert that to a p-value. And like with chi-squared, we need to pay attention to degrees of freedom, which has to do with our sample size. F statistics are actually particularly weird. We need 2 degrees of freedom. One of them measuring how many groups we have, and the other measuring how big our sample is. We can see that in our table here as well. This first degrees of freedom is the number of groups minus 1, and the second degrees of freedom is the total number of samples we have minus the number of groups. So this pair of degrees of freedom specifies a particular distribution. And just like with the chi-squared, our question is always going to be, what is the probability that we get at least 44.8, at least our F score, on this particular distribution? So if we were to run this test again, if the null hypothesis was true, if all of the different sprays actually did the same thing, then the probability that we get a similarly notable sample is going to be the p-value, which comes from the area of this region. In this case, since our p-value is extremely small, we reject the null hypothesis in favor of the alternate hypothesis.